Hello and welcome everybody to this webinar, Understanding DECT NR+, the first non-cellular 5G standard. Before we get started, I am Heidi Soli. I'm Product Marketing Engineer responsible for DECT NR+ at Nordic Semiconductor. And with me today, I have Lauri Pikivi, who is the Technical Product Manager for DECT NR+ at Nordic, and he's the one who'll be giving the presentation today. Some practicalities before we get started. This webinar is approximately 45 minutes long. That's 30 minutes for the presentation and then 15 minutes for questions. Please ask questions. They're highly encouraged. You can ask your questions in the top of the right sidebar. There should be a panel called Questions. All questions are anonymous, and we will answer them at the end of the presentation. The chat, however, is not anonymous, so please do not use that one for questions. If you have any more questions after the webinar, or if your question wasn't answered, please go to DevZone and ask them there, and we have a very capable technical support team who will try to answer them. And a recording of this webinar, as well as the presentation, will be available at webinars.nordicsemi.com. And with that, I will hand it over to Lauri.
Thank you, Heidi. So my name is Lauri Pikivi, and I'm the Technical Product Manager for DECT NR+ radio technology here at Nordic Semiconductor. So the agenda in short for this presentation is what is this NR+, what are the benefits, how does it work, how does it achieve those benefits, and then short look at the current status of the standard and implementation before the questions. And then the what are we talking about? So NR+ is also known as DECT 2020 new radio. So it has these two names. It's the same thing. NR+ is the marketing name. DECT 2020 is the working title that was used in ETSI during the standardization. But that year came and went, so it's not a very good marketing name anymore. So we talk about NR+. And how did we end up with this new exciting standard? So we didn't intend to make life any more complicated than it is, but there was a chance of using existing spectrum allocation with a new radio, utilizing the best of the cellular technology developed. And we ended up with a new radio standard. And what this standard achieves and why it's called non-cellular 5G is that it actually fulfills the requirements that the E2T, which is standardizing the 5G and making the requirements. So DECT NR+ is the first technology to actually meet these requirements for massive machine type communications, so large sensor networks, for example. And then the ultra reliable low latency communications, where low latency is the key and can be used, for example, in automation control or factory environments. So DECT NR+ meets these requirements and is therefore a 5G technology without a network operator. We'll get back to that one. So what are the key benefits of NR+ is speed and latency. So speed, we can achieve 1 to 3.4 megabits per second on our implementation hardware and current implementation. The standard goes up to gigabits, but then you need to have higher frequency spectrum allocation and so on. But that is certainly there available when the standard and technology evolves. So we start with the 3.4, which is not a bad number in itself. And like I said, the latency, it can achieve like 1 millisecond latency for one link. So in the star network, kind of easy to meet those latency requirements. And then on a mesh network, it gets a bit more complicated, but you can still get very short latencies even in a mesh network. It's low power. It has some unique features. We'll go in detail that enable low power operation. It's a mesh network. So we talk a lot about the mesh networking side of it. We don't necessarily have a mesh network, but we see mesh networking as a key thing here because it's kind of self-expanding network, increasing the range as you add devices. It's self-healing, self-load balancing, so very minimal network maintenance is required. And one of the key reasons why we started this whole exercise is the frequency spectrum. So DECT has been around since 1990, and it was used as the technology for cordless telephones, and it achieved, or it was granted like a global spectrum to operate in. And it was then kind of noticed that, okay, there isn't all that much use for that spectrum anymore, but the spectrum is there, and we implemented this new standard to utilize that spectrum for IoT purposes. And then a look at the protocol layers and how does it actually do what it does. So first, some vocabulary. So we have a star network and a mesh network. In mesh technology, basically all the devices in the mesh network can route data on behalf of other networks. So they can extend the coverage by receiving messages and then forwarding them to their child devices in this kind of tree mesh. And to be exact, DECT NR Plus is this partial mesh topology, a clustered tree when it is a tree. And I will be talking a lot about these routers and leaves and parents and childs. So parent is always a router device, and a router device can have its own parent, which is another router. So you go up the tree, and then leaves are devices that don't have any additional leaves, so they are the end of that branch. When I start talking, I usually mix up these kind of terms of gateway or sink or border router, which is like the root of the tree, and then the relay nodes or router nodes or parent is the same thing, and then leaf node or child node is the same thing. So please try to follow my speak when I mix these terms. Sorry about that. So a very high-level overview of the network layers or protocol layers on the DECT NR Plus. So it has 4 layers. We will be talking of the convergence layers and data link layer. Most of the talk will be about the medium access control layer, because that's a very central thing in DECT NR Plus. And there is a physical layer with OFD and technology and all sorts of nice stuff, but that's not my area of expertise, so we will mention it here only, that there is a file level underneath all these other labels. And then one thing to note here, that DECT NR Plus is like a radio and meshing technology in itself. And if you have worked with internet protocol based mesh networks, then internet protocol is just one application choice on top of the NR Plus from NR Plus perspective. So there might be IP stack running on top of the NR Plus or applications directly. It's mainly how you do your network. So do you have online network connecting to backend, then IP makes it simple, but then IP can be also done from the sink or border router towards the network. The system is for the application developer to define at this time. So all this operation here is something that is defined by NR Plus and can operate underneath IP addressing. Convergence layer and data link control layers are the two topmost layers there. Convergence layer main functionality is this application multiplexing, so directing the traffic for separate applications if you have multiple applications using the stack at the same time. In embedded devices, you usually have just one application. Of course, the convergence layer also is the kind of access point to the whole stack. So the DLC level transport service selection is there. So do you send those messages as transparently without acknowledgements? Do you segment the message to get it in parts through the network? Do you have like an acknowledgement for those messages? That's on the DLC level. And then the DLC level handles routing of the packets. So we go a bit into the details on the routing. As the routing is defined now for the NR Plus underneath the IP level. So going up the tree is always very simple. You have one parent as it is defined now as a cluster tree, and you always send data going to the sink or going to the back end. You send it to your parent, and the parent will forward it to its own parent, and then it reaches the sink, and the sink can then do internet protocol communications or like gateway operation, changing the radio bearer to cellular bearer or ADSL or Ethernet or however it's connected to like the backend systems. Upwards routing is simple. Downwards routing is where we get some of these unique features from NR+. So NR+ doesn't have a routing table in the router devices or in the sink device. So when you have a packet going to a device in the network, the sink, if it doesn't know directly that device as its own child, can only forward that message to all the routers that it knows. And then the routers forward that message to all the other routers beneath them. And at some point, the message comes to the final router that knows that, okay, it knows exactly that this device is its own child. And at that point, it just sends it as unicast to that one child, because that's where the routing happens in the cluster level. You can say that this is a bit wasteful of the radio resourcing, but the nice thing about this is that it works very well, even if you have errors and changes in the network happening. Very often in mesh networks, you have changing radio situations, so the devices move from one router parent to another. And if you have more advanced routing algorithms in downwards traffic direction, then you would need to have additional signaling. Now in NR+, the switching of the parent is instantaneous. You just tell the new parent that you're associated with it, and that parent will then forward any messages that will come to it to you. And that makes some interesting use cases for network mobility. There is defined like flooding mechanism from one leaf device to another leaf device, for example, within the mesh network. And it's flooding based as well, and it's hop limited, so you can set how many hops there is. And then when you increase the hop count, at some point you will reach the other device, and then you have established that path. But from one device to another, like horizontally within the mesh is a rarer use case, how we see the application, so we don't go into details on that one. MAC level of the stack. So MAC level is very central. There are some specific features that we will go through in the next or few next slides. So we have, on high level, we have broadcast, multicast, or groupcast, and then unicast possibilities in the radio communication. You can have dedicated flows where you reserve the radio resourcing for that communication, or you have this random access competing kind of access to send the data. Just a short note on the addressing or IDs of the devices. So it's 32-bit identifier for the radio within the network. So you could have 4 billion devices for a really huge network. But I mean, the addressing is not a limiting factor for sure. We will talk about the beacons, which is a central thing for this MAC level. And then the MAC level also does this kind of hybrid acknowledgement on the file level for hop-based acknowledgements. And if the data packet was received correctly or it wasn't. If it wasn't received correctly and you have selected this kind of acknowledgement transport quality, then there is a resend, and on the file level it uses forward error correction and like soft combining. So it combines these different messages that it has received, and it can kind of achieve a complete correct message even if it has only received a few messages with errors in them. So that's a very nice feature on the NR+. But about the radio resource control, which is the main functionality of the MAC level. So it is based on these beacons that a routing or relay device sends. So the routing or relay device is responsible for that radio resource management within its own cluster. So the cluster is basically the range of its own radio where it has child devices and it may have like a parent device. But that parent device is running its own cluster, so then this routing device acts as a child to that its own parent. But the radio resource control kind of mandates that the routing device, it scans the whole, or it scans the channel usage a few times during the beacon period. And it can then tell the child devices when it's safe to send and when itself is prepared to receive traffic. And for a leaf device, they must follow this guidance from the parent. And then when they are competing in the random access channel to talk with that parent, they must do this kind of listen before talk. So listen before talk, before sending, and if you detect that some other child is already talking to the parent, then you do like a incremental backoff with randomization, and then you try again if it's free to send on your turn. So a bit more details on these beacons. So this is like a map of the radio usage. DECT NR+ has 10 millisecond frames, and these frames are then divided to 24 slots, like time slots. So it's channel and time divided, this kind of access. And on these time slots, the routing device, the parent device, will tell if that radio can be used and if the parent itself can be reached on the radio. So because it's based on these beacons, so the beacons of course take some space from that radio resource. And if there is like a parent to the parent itself, then it needs to tell that, okay, at this beacon time, at minimum, it's not there because it's listening to its own parent on the parent channel. And then the routing device, the parent device, can page the children. If there is data coming to that child device, it will tell in this paging window that please be awake at time slot 10. I have data coming your way. And then the leaf device will be awake at that time point to receive the data. And a very critical thing is then also this, what is shown as green here, which is the random access channel time window. So the parent device advertises that it's available within this window for random access from the leaf devices. So when the leaf device needs to talk upwards, they will use this random access channel and random access window to talk to the parent. And shown here is also additional kind of like reserved time slots, which is, it can be like a dedicated flow reserved for a certain device within that cluster, or it can be like a detected legacy DECT transaction or like a call happening there. So when the parent has scanned the channel, it has detected that, okay, there is this kind of peak in the power on these time slots. So it assumes that there is like a legacy DECT happening there, and it will tell the child devices that, okay, please don't use these time slots. We let the legacy DECT do its stuff, and then it can take these time slots back into use. So one nice thing about this beaconing and this kind of rack window advertisement is that it actually allows the parent device itself to have power saving mode. So that's very rare in kind of mesh networking. And of course, it's a compromise or like a compromise between power usage and then your kind of latency requirements and the kind of amount of data that you need to send. But it allows these kind of scenarios where the parent device can say that, okay, it only has like a partial rack window available for the child devices, and then it can sleep at the other times because it knows that it hasn't advertised that it would be there, so the child devices will not try to talk to it within those time slots. And you can play around with these kind of setups according to your application needs. And basically the beacon itself, it can vary from 10 milliseconds to 32 seconds when you send that beacon. So that's the kind of windows that you're looking to allocate the resources for. And if a child device doesn't have anything coming down to it, or it doesn't have anything to send, it only needs to be awake to listen to the beacon. It can verify that the network is still there and verify if there is any data coming down its way. And if there is nothing, then it can go back to sleep. So it will be awake for 1 millisecond every 32 seconds, giving a very good power saving possibility for these kind of leaf devices. Then like a stack view, how these different levels work when forwarding the traffic. So you have a leaf node and you have a sync node. And of course, on the convergence level, if you have, for example, the encryption on the CVG level, then that is between the leaf and the sync. And midway, or these relaying nodes, there can be multiple, of course, in a mesh network. The data just comes and goes on the routing level, where it's noticed that, okay, it's going upwards, and then it's forwarded up to the parent, and it reaches the sync. So very limited kind of operation here on the intermediary relay nodes on forwarding the traffic. Then a few words of the dedicated flows. So, like mentioned, this is a possibility there in the standard. So a leaf device will basically reserve certain amount of that radio resource. Let's say that it needs to talk 2 slots every 20 milliseconds. So it can do this kind of reservation to its parent in the association or association modification. And the parent will check that, okay, does it have the resources available? Is there still radio resource? Does the parent itself have like processing power to ensure that this will happen? And it will then acknowledge or reject the kind of request. And usually you make your system so that it's accepted, so you get that dedicated flow going. And when you have a dedicated flow, then you actually need to send on all those slots that you have reserved. If you don't send, if it's noticed that the slot is basically empty, nothing is received, then it's assumed that, okay, this dedicated flow is now ended and those resources can be given out for other leaf devices to use. But for example, if you need to do this kind of low latency communications, then the devices can ask their own slot, and the sink will then just share the radio resource. All the leaves have their dedicated slot that they can use, and then they either send measurement data or whatever data, or they send this kind of padding data, which is just used to keep that reservation going, but don't contain any kind of application level data. Dedicated flow is per link, so from leaf to parent. So it's very easy to do in this kind of star network. And then if you go into mesh networking, of course, the parent is a child to another parent, so it can then forward this kind of, or make its own reservation, but you can end up in these situations that you would need to then negotiate that there is some link that is very heavily used and you can't make it end-to-end. So then you will need to do some proprietary stuff that is not currently defined how you do this in a mesh in a reliable way. Look at the standard. So like said, the standard, the technical standard is defined by ETSI, the European Telecommunication Standardization thing. And what there is now defined is a lot of features, which are these Lego building blocks. And then you can have profiles, which are like commonly agreed for a group of applications that then define what of these building blocks are used and how. But the aim of DECT NR Plus is really this kind of application defined network. So the networking is just like a feature of that application, because they create the network as a mesh network for themselves, by themselves. You don't have a general network that some operator would be running. And because you don't have that kind of general network, you make your own network, then there is no real point in interoperability specification. So there is none. So when you select what features you use in your application, you kind of select how your very specific network works, and you can make it work because it's for you, it's for nobody else. So these standards have been now a bit over a year publicly available. So they are open standards. You can download them freely from the net. There are a few standards. The overview is a very good standard to begin with. It explains the high-level operation of all these different standard documents. We are now in version 1.4.1, so there have been some corrections, and errata is still expected for this 1.x release of the standards when the implementations happen. And what we are working on in the standardization is like a harmonized test specification, how to meet the regulatory requirements and ensure that different DECT NR Plus networks can operate in the same location. That's being defined. It should be finalized towards end of this year. There is one application profile in the making for smart metering over NR Plus. And then there is gathering of requirements for like the release 2 of the standards, what new features need to be done there. Then, of course, interesting question, what is the implementation? So Nordic is talking about DECT NR+, so it's no surprise that we are working on it. So we are working on the PHY-level software, and it's like a software variant for our NRF91 series. So it can be flashed there to replace the cellular LTE-M modem that the 91 series usually has. And because we are working on the PHY level only, we have a partner, Wirepass, who has the rest of the stack. So the Mac level and upwards. And Wirepass have been working on meshing technologies for a long time on top of Bluetooth with their mesh stack, and then now porting it to this DECT NR+ radio. And there are some other partners that we have for other use cases and kind of low latency communications and audio-centric communications that they want to work on. So they are building on top of the Nordic PHY. The Nordic PHY can be licensed. We don't charge money for that software separately. We sell the system in packages. So it can be licensed, and we need to license it separately because it is a PHY level only. So it doesn't meet the harmonized standard by itself. And that's why we want to control how it's available for people and companies in the world. Then a lot of the questions, like I said in the beginning, can be answered in the dev zone, where we have our support channel. We have a dev academy for a lot of our technologies. For example, the Zephyr operating system that we use for all our system in packages. And then, of course, we run these kind of webinars. But that's it. A very short overview of the DECT NR+, and faster than the morning thing. We still have some time for the questions, actually.
Yeah, we got in a few questions here, so I'll just ask them one by one.
Yeah.
First question, can there be more than one sync in the network?
Yes, that's a very good question, and yes, there can. So you can have multiple gateways out of the network, meaning that there is no single point of failure. So, and they balance the load basically within that network when the devices see that there is a routing cost available from some other gateway. So they kind of share or divide then between those gateways as the radio links allow. But yes, there can be multiple gateways.
Okay, what are the advantages of DECT NR+ over Zigbee and Thread Mesh?
So Thread Mesh currently is operating on the 2.4 gigahertz ISM band, which is congested and has issues out in the wild because of that congestion. So we see this spectrum, 1.9 gigahertz spectrum as a big asset for DECT NR+. And Thread is a nice meshing technology. I've worked on it myself, and you can do a lot of stuff on Thread. But for example, if you want to build these kind of massive networks with really a lot of devices in them, then Thread has some limitations that you currently can't overcome with like the addressing space, for example, for the devices and the limited amount of routers, because it has a more advanced routing thing. So here, the DECT NR+ simple kind of brutal approach to routing actually works and makes these kind of large networks possible. What was the other technology? I forgot now. Zigbee. Well, Zigbee is very similar, in my opinion, to this Thread kind of approach. Zigbee is more for industrial things. It's an older thing. So Zigbee, I think, has the biggest problem in the bandwidth, or like how many megabits can you get through it. So now DECT NR Plus expands on that speed, and you can do new stuff and more advanced stuff on top of NR Plus.
What are the methods to choose the sync in the network? Is there voting implemented in the stack?
Well, no, there is no advanced voting kind of mechanism. So sync is the device that starts to advertise the network and test that its routing cost is 0, basically. So the sync has a back-end connection if it has one. You can have also like offline networks, but the sync starts advertising, and by the routing cost, it will be the sync. So then other devices will hear the network advertisements and will connect to that sync, and then they expand the network, but the routing cost will increase. So the first one will be the sync, and I mean, it's a simple kind of approach that works. You can do it more fancily like Thread does, but that has been considered like unnecessary at this time.
And then there's a question about, will Nordic Semi have a dedicated chipset for DECT NR Plus? I'm not sure.
So we don't currently envision like a dedicated chipset. So like I said, we are now working on using the 91 series, so which is like an established chip that we have in the market. And we see that for the foreseeable future, this is like a software variant on those chips.
Once the network topology is fixed, is the latency relatively fixed, or is it arranged?
So when the network is established, you will have variation in the latency for mesh networking, because there is this kind of congestion on the radio usage, and you can still end up with this kind of situation that like a legacy DECT does something nearby, and it will affect that dedicated flow if you've set up like a dedicated flow. There are different kind of approaches in the standard how you can actually talk between nodes. So you can achieve really low latencies, but it's a radio technology, so you can't guarantee it in the end.
Here's a good question. Are there interfaces in the standard to integrate a non-cellular 5G DECT NR Plus with a cellular private or public 5G?
So that would be like a sync device. So it would run this kind of mesh network or DECT NR Plus network, and then it would have another networking interface, which is it can be like an LTE or 5G network. But that would be like a device which runs like a private mesh DECT NR Plus network. We don't envision operators, like cellular operators, to start building these kind of networks to offer it as like a general network for you. Like I said, there is no interoperability standard, for example, that it would need still some standardization to make that kind of thing work. But we look at these device-specific, customer-specific networks that they build for themselves, and then connect from the sync to whatever mechanism that they use to backend connectivity.
With LoRaWAN, there are concerns about interference from other nearby LoRa networks. Does NR Plus offer advantages over LoRaWAN as it relates to interference?
So interference is there, but it's minimized. So when a routing device or when like a sync establishes network, it will scan the different channels and it will select the channel that has least interference or least usage. So that's one way. It's OFDM, so it's orthogonal, whatever magic that is on the file level. So the networks will basically not see each other. It's just like small increase in the background noise between different networks. So that's one mechanism. And then, of course, there is this kind of avoidance of the busy slots that are detected. And then they can dynamically change the channel. So if the channel gets worse and worse and the routing device scans different channels and notices a better one, then it can advertise that in a few beacons, I will be changing channels to another channel, and then the child devices can follow.
What is the leaf to sync latency expected in a DECT NR Plus network?
That depends very much on the number of hops and then this kind of radio resource policy that you define for your application. So upwards, if you have these kind of constant random access windows advertised by the routers, basically you can have like a few milliseconds delay from the child to the parent. And then that parent can also have a few milliseconds to its own parent. I'm saying a few milliseconds because there might be that beacon there, or there might be some other device sending at the same time, and you need to do this listen before talk and back off. So it might be a few milliseconds per hop. That's one possibility to make it.
And then I guess this is the last question we have the time for. Router or parent devices, are they always powered devices or can they sleep?
So like I said, it's one of those interesting things in DECT NR Plus is that you can make them sleep, which is very unique for a network. Of course, it's much easier if you can say that they are powered on, and then you can have these low latencies and big throughput for that network. But it is possible that you can say that they are sleeping part of the time, and that, of course, then cuts out of the radio resource usage that you can do. But it's possible, a unique feature.
Okay. I think I said the last question was the last one, but I think we have time for one more. How common is the open 1.9 gigahertz band used in NR Plus between the EU, US, and APAC?
So it's there for EU and US. And then in APAC, it depends. One big thing there is that China doesn't have that allocation. They've used it for other technologies. But outside of China, then you usually have it. Like a lot of Asian countries, they follow EU legislation or like these kind of radio standards, or they follow American standards. So basically, it's then available in those countries. But there is minimal kind of variation there. That is it 20 megahertz spectrum allocation, or is it 10 megahertz spectrum allocation? And it's 1900 megahertz plus or minus 20 megahertz where that spectrum space is, but very close to each other, like in different regions.
Is DECT NR Plus specification open? If so, where can it be obtained from?
So it is open. The ETSI standards are open. So you can find it from the ETSI web pages, or Google is very good. Google find it very easily, and you can just download it. No registration, no payment, nothing required.
Is DECT NR Plus similar to Bluetooth Low Energy? And could we think that DECT NR Plus would replace Bluetooth Low Energy, for example, in the coming years?
I would say that they are very different. I mean, both are low power radio communications, but the DECT NR Plus is really made for massive IoT mesh networking, and Bluetooth is much more oriented in this point-to-point communication. There is a mesh networking solution in Bluetooth, but it's very limited in operation and bandwidth compared with DECT. So I would see that DECT has its own space in the market, and well, markets will tell.
And I think the last question we have time for today, can we say that this is perfect for moving nodes since leaf attach is claimed to be instantaneous?
So it is very good for moving nodes. So of course the node needs to be scanning the network or radio channels to detect new parent that it could move to. But then if it detects one, it can move there with this one association request just to tell that it's now there. And there is a mechanism in the standard that a router, if a routing device detects other routers, it can give kind of pointers or hints to the leaf devices that there are these other routers available on what channel and what beacon time do they have to ease the mobility. But in the basic form, because it is so fast to join the network or move from one parent to another, it makes it very good for mobile nodes.
Okay, thank you. And thank you everybody for joining today's webinar.
Thank you.